Okay, today's lesson is lesson number 12, and the topic is the number E. So we will try to see what is this E supposed to be. And then the goal of the lesson is I know that E is an irrational constant like pi, which pi is an irrational number, which is actually circumference divided by diameter, which represents 3.14, and which is rounded up of a irrational number. Likewise, today's lesson is about understanding that E is 2.7182. So starting with the first uh, activity, E is about, we are given 5 equations F, G, H, J, K. And now I just imagine I don't even know whether these 5 exist. I'll just go straight away with the first question and then create my own. Let's model into a mathematical equation, the first one. And let me, okay, so this is the first problem. So you can read nicely, underline whatever important information there. So let me take straight away here. So the first one is the scientist begins an experiment with 400 bacteria in the beginning. So that means in the beginning, that's like a A. So I want you to write down this way so that you understand what is that A, because the equation y is A times B raised to x. And when x is 0, 1, 2, like this. So increase of x is, when the input increases by 1, so that's the A part. A is 400. And the next question is the population doubles. So I will underline that's important. This is the population doubles means twice. That means that itself is the growth factor. So I'm just going to write here this is growth. So that's the growth factor. And this growth factor is for every 10 hours. Now, I would like to make a table so that we understand the visuals. So no matter how smart we are, it's always better to write like this. Okay, in the beginning, T stands for the number of hours. And let's say the population start with the P letter. I'm going to write P of T. So imagine I just don't know what is the 5 equations there, but I'll just write down like this. So I want you to draw each of this problem is to create a table, visual understanding what's going on. Now every 10 hours, so this is a group of 10 hours. So from here to here, group of 10 hours, the population, which was 400 in the beginning, this doubles. Now, what is the meaning of doubles? Means the growth factor, so GF stands for the growth factor, is given to is 2. So you already know, of course, in the equation, look at the equation that I gave you. This is for, this B is growth factor for every 0, 1, but here that 1 is like 10. So this is like 1. 1 means when x is 1 means 10 hours. Uh, so so doubles means 400 becomes 800. So growth, this two growth factor, which is actually 100% increase here. Okay, but the question is we want to create a function that is gives the number of bacteria T hours since the experiment began. So we need to now no, so I'll break this into 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. See, 1, 2, 3. So that means we need to know every hour what's the. So that means we want to know the B for. So the B that I'm using in the formula, this B has to be for. This B is for each hour. So each hour. So that means when I go back here. So we need to know what is that number that multiplies from 400 to 1 hour. What number multiplies? Then again from 1 hour to, so we don't know this, so we'll put it like a B. So there is a B, this way you go on multiplying B 10 times. See, so B, there are 10 of these pieces. So that means So that means B is multiply itself 10 times. And when you multiply 10 times, you get a 2. So this is 2. So by definition of radicals, this is equals, even though it is a square 10th root of 2, actually it is 10th root of 2, but I'm going to write it as 2 raised to 1 over 10. See? So that means in the formula y equals a times b raised to x here, now it is p population after bacteria population after T hours, what you have in the beginning, that is 400, and then each hour it grows by 2 raised to 110. See? And the whole everything raised to, instead of x, it is T here. That means now we can write this as, this is, so this is 400 times, and instead of, so that becomes 2 raised to multiply 1/10 of t, that is t over 1 over 10. But in the decimal form, we can write it 400 times 2 raised to 0.1 multiplied by t here. See? And then if you see this, this exactly matches the one of the five there, the last one, which is also k of t. And that completes the problem. So we model the whatever the situation, real life situation, we modeled into a exponential function, this one, and this we created, but then it is the same as like kt, and you're done. So that takes care of the the first description. Okay, the second question is, a patient takes the medicine. Oh, this is about medication given in the hospital. Let's say 400 milligram of medicine is being given, and this amount of medicine in her bloodstream decreases by, now this word is very important, decreases by 25%. So 25% decreases basically means 75% stays. See how it is? So this stays. So 75% stays because 25% is gone. So how did you get this? This is 100% minus 25%. It's like you go in the store and there's a 25% off in a sales. Then you say you end up paying 75%. Now 75% is also 0.75. So So in the formula, when we write y equals a times something here and x, so the b, this b, this part, even though it is b here, we need to know every hour because this is in the group of 10 hours. See, this is again the same idea. So in the beginning, 400 milligram is given, and in 10 hours, that becomes half, 200. See, half of sorry, it doesn't become half, it's 75%. So calculator gives you, if you try to use 0, so what multiplies is 0.75. When you multiply to 400, you end up getting 300, and it has to be because 400 is 100, 100, 100. Okay, so if I break this into 100, 100, see, and if I take one of this piece away, so what remaining is 300, 3/4 of 400. So this is growth factor for every 10 hours, but we want to know for every 1 hour what is the growth factor from here to here. See, so that's the B part. So B, and likewise, you have to have 10 of these pieces. So B raised to 10 is, see, so that means b raised to 10 is the growth factor. This is the 0.75. So that's 0.75. And use the definition of radicals. So b is 0.75 raised to 1 over 10. Okay. And this is what growth factor, this is growth factor each hour. So that's so important. This growth factor is for every 10 hours, for every 10 hours. So that's different. But in the formula, this is where the B part, this is the B part which goes straight away here. Look how beautiful this is. So, and because this is T hours and this is, let's see, this is the amount of A of T, I can just make my own letters here saying amount of medicine in the bloodstream, T hours since it was administered. So that piece becomes A of T. So A of T is in the beginning 400 milligram of medicine was given, and then the growth factor is for each hour is 0.75 raised to 1 over 10 and the whole raised to t. See, this is the beautiful thing is this, we are talking about number of hours since the medication was given. So you put instead of x you put t, and that is same as this is equals 400 times we can multiply the power of power means you multiply uh, 1/10 of, that's like 0 point directly we can say 1/10 of means 0.1 times t and you're done. So this is very important, and then you can say, hey, where does this match, which letter does it match in the packet? Look which one matches, and you can see from it becomes 0.75. I think it is h, right? Correct. So you see this is h of t and you're done. So it matches the function that is given in the 5 option. Okay. Question number 3 says this talks about half-life. Half-life of a radioactive element is again you have a we can make a table like this 10 years. See, so from 0 in the beginning it is 400 grams, and in 10 years it become half, that is 200. So this is like 10 years. So in 10 years, the decay factor, I call this as decay factor, because what number multiplies is 0.5, because half, right? So half-life basically means whatever the radioactive substance becomes half after a certain period of time, but they gave it 10 years. So T stands for how many years since the uh, studied how what, in the sample there was 400 milligram that in the certain year, and then they went on studying and seen that in 10 years it becomes uh, half. So this is amount of substance, radioactive substance in the sample studied. So so what's given here? This is the decay factor for every 10 hours. This is for 10 hours. So the formula y is a b raised to x. You already know what is this a. Uh, so the amount of substance, radioactive substance in the beginning is 400. So the a is 400. So they already know. But the question is, how do we figure out b? And b is what you do. Okay, b to b. So these are all 10 times you multiply, going on multiplying 10 of these pieces. So same thing what I was showing, b raised to 10, this time it is 0.5, the black color 0.5. So this part. So so growth factor. That means b is 0.5 raised to 1/10. Okay. So now we want to know what is this amount of, sorry, a of t equals. So we can use this formula. So a is 400, that's what we have. Then times, and I put a bracket to show, and t outside the number of years since it was studied. So we got the answer for, we got it as 0.5 raised to 1 over 10, which is same as 400 times 0.5, but then we can 1/10 means 0.1. So this piece, so this piece is 0.1. So I'll just write 0.1 and times t. And that's it, and you're done. So this is the new mathematical model of the real life situation. And if you see on your paper, it shows which option helps you to identify this is. You can clearly see it is f of t, the very first one. So this is how you have to figure out. I hope this helps. Correct. So question number 4, in a lake, the population of species is, so put this as A, there you go, you got the first one correct. The population is expected to grow by 25%. Now, what this means is, if you draw the table, let's see this piece. So in the beginning, it is 400, and then in 10 years, this is 10 years, it is expected in 10 years, the population grows by, now when you say grows, what does grows by 25%? It means you had in the beginning, whatever the original one, 100% plus 25% together is 125%. And what is 125% means? It's 125 divided by 100, which is in decimal 1.25. So this is 1 point, the growth factor. So this is the growth factor for every 10 years. But when we want to create an equation, we need to have every year. So I'll have to break this into 1, 2, 3, 4, 5, 6, 7, 8, 9. See, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we want to know what's the decay factor for each year. This is like 1 year. So if you go from 0 to 1 year, it is B. We don't know 0 to this. So like this, there are 10 B's there. Okay. So all these 10 B's. So it's the same thing, but different situation. So let's write it here. So the formula is y is a into b raised to x. So a is already known, and the b is also we already got. No, b is what we have to figure out. What is this b? B raised to 10 is 1.25. That means B, by definition, B becomes 1.25 raised to 1/10. And 1/10 is also, we can directly write it 1.25 raised to 0.1. I don't have enough room to write there. So let's keep it 1/10. Now let's see. This is T years. T is number of years. And AT stands for amount of radioactive substance remaining in the samples studied. So the equation becomes A of T. So equation A of T equals what you have in the beginning, that is 400. Then each year it grows by this factor 1/10 raised to T. And that is same as in decimal form 1.25, that is 0.1 times t, and that takes care of that last one. So you can clearly see this is how beautifully we can model real life situation. Problems can be modeled into exponential function like this, depending on different decay factor. So in this case, it is growing, so there is a growth factor, percent increase, and so on. So let's move to the next one. So the question is 12.2 says three representations are being shown. One is the table, the other one is the grid of graph, and there's one equation is given here. Look at this equation AT. So the question is, what do you see and what do you wonder? So you can write a statement by yourself. So I hope you have written down something there and check your answers. So one thing you notice is I will just hold on with this equation and say, hey, is there any connection between the table and the graph? And you can see there the 0, the input 0 and 10, this means it's like there's a point right here. It's almost like matching here. So can you write this on your paper? That means this piece is 0 is 10. Then the next one is 1 E, that means after 1 week there is a 27, and you can see the other piece, this dot, this black dot, it means this is 1 is 27. Then the 2 is 74. So this matches. See, what you see is the table matches with the plotted points in the grid or the graph. So 2 is 74. And the 3, the next one is 3 is 201. So this is almost little above 200. So 3 is 2. Okay. And now for 4 weeks, 576 is too large. So we don't have anything there. So I can just extend maybe and say this is 300, this is 400, that is 500, maybe somewhere here, maybe a piece. And you can just extend that. You don't have to do on this on your paper. I'm just saying, okay, this graph it's like goes this way. See, it goes this way. It's like 4 is whatever that 546. Okay. 546. So there is a relationship between the table and the graph there. Another thing that you can notice is uh, those two are there is a, you can also see is the what is the growth factor, what is the factor multiplies on your calculator. If you see from if you do 20 like 27 divide by 10, you get 2.7. So this is like you multiply 2.7. Again, if you multiply this 74, if you do 74 divide by 27, I think it is like 2.71 or something. It will be something like that. I'm not sure. You can check with your calculator. Even this will be, so this is 2.71. Maybe this is 2.74 or something. This means 2 point maybe 2, anything, but it's always 2.7. That's a good news. So each of this, when you take the ratio, the number gets is 2.7, almost 2.7. So this is the growth factors. It looks like the table is exponential. Table represents the exponential function, and the same thing. This graph, by the looking at the shape itself, is this is exponential function. So it is the graph of exponential function, representation of exponential growth of function. So I hope these few things understand. So we see that there is a 2.7 which always gets multiplied. So the question is, so what is this 2.7? Okay. Now check the equation. Now in the equation you see there is a 10. The 12.1 that we did was because we would be able to do this. In 12.1, there were 4 description, and each of these 4 description, we try to use a times b raised to x. And and this is what the 10 is right there. So look at this. This 10 which is right here. So this 10 is right there. Look at this. This is that 10. This is the 10. But the question is now I want to relate this to this piece is 10 times something, and they give you the E. Now, what is this E? So the way we see this E is like a growth factor. So this is growth factor. And we have seen from all those pieces that we did there. So here you've seen this. Each time you take the ratio, it's almost little more than 2.7. So I'll just write 2.7. Again, you multiply 2.7. Again, you multiply 2.7. Again, you multiply 2.7. It means every time you multiply little more than 2.7, they are not exactly the same because whatever the number they show here is they are not they are rounded number to whole number, so it doesn't give you the actual square centimeter. But the point is trying to connect, oh god, this E is same as 2.71. So the E, if you compare in the equation with this, so if you compare this in the equation, it's like E is 2.7, 2.7 and little more. We don't know what is that, but we will see that this E basically is the first letter. This is the first letter of second name, second name, second name of mathematician. I think it's the 16th century. No, no, I think it's 17th century mathematician, French mathematician. His name was Leonardo. Leonardo Euler, Euler. So in his name, this E starts there. So they say, okay, that E is just a number, but it is a constant. It is a constant. It is a number. It is also an irrational number because it's in decimal form, which is 2.7182, and it goes on. It does not have a pattern. It's just random numbers without stopping, or endless numbers, non-terminating, never-ending, uh, non-repeating and non-terminating. So this is an irrational number. So how this will be? This will be E will be a number used in the later class. It's used in engineering or in also in research. It is being used, and we will see a lot of this in the coming classes. So hope that helps with this 12 point. Okay, hello students. I would like to continue this. This is we are on 12.3. So 12.3, here are some functions. For each function, describe in words the outputs for every tiny positive value of x and for a very large value of x. Now, the first one is given. I already used the snipping tool. That means your a x raised to 1 over x. And remember, this function, anything raised to 1 is just a 1. It means no matter what is the input, uh, let's see if this is 2 and if this is 1 and 0.05 or 0.1 or 0.01, your output is always going to be 1, 1, 1. And same thing as you go and make very large, let's say it is 100, this is going to be 1, even if it is 1 million like this, the answer is going. So for for small value of x, for small value values values of x, and also for large values of x, the output x will remain the same. So that's the will remain the same. So this is the understanding of. Now, graphically, I'm going to show also on Desmos what it means is it is the line which is y equals 1. That means whatever this point may be, the input on the thing. So if it is 0, it is 1. If it is 1, it is 1. If it is 2, it is so all these points get a line. Okay, so that takes care of the first one. Let's do the. So what does this be? Here you will see b raised to x is negative x. So for small positive values of x, okay, so if I start with very small, let's see, if I take the, let's see, 1, 0 0.5, 0 0.1, 0.01, and 0.001, and if this is x, then the bx is negative x, okay? So the input will change it to negative. So if this answer will be 0.001, this answer will be zero point zero 0.01, this will be 0 point, and so on. So all it changes from positive, it changes to, that means if you want to see the graph of this, so the for small value of x, the input values becomes the opposite of the input value. So the output is the opposite of the input. And the same thing if you make it larger, even if I put 10 and 100, so it doesn't matter, 1000 and so on, 10,000, the output is going to be negative, no matter whatever that is. So I hope that makes it clear. So that's what the bx equals negative x. If you want to see the line, and remember this is if in the slope interval it is minus 1 over 1x plus 0. It means the graph is that the slope starts at 0. The slope is negative 1. It means you go down 1. If you go 1 down, you go 1 right. So that means you go 1 down, you go 1 right. You go 1 down, you go 1 right. And same thing, you can go 1 up and you go 1 left. So this is the line. Can you clearly see? And this is the point when x is becomes a very the input becomes very tiny positive numbers, then the output is become also tiny. They become larger because they are negative, but they almost uh, equal to 0. So you can see these values. Of course, this number is bigger than this number, but then they become very uh, the number almost approaches to 0. This number is bigger than this number is bigger than this. But for tiny values, as x approaches very close to 0, this also number approach very closer to 0. That's the understanding. Let's move on to the next. Now, for the third one, f of x, all we have to check is if I put, we can't put, if so for x equals to 0, so f of 0 will be 1 over 0 raised to 0, and this is undefined. So there's no value of output when x equals 0. That means if I want to graph this, and if this is the one here, then what's going on is for different values. This is 1 and this is 2 and this is so. So the graph at this point 0, the graph approaches something like this. So approaches to, so this is 1, the graph, we will see on the Desmos also, this graph will look like this, something like this, goes like this. When it is 1, if you see, if I put 1 here, 1 over 1 raised to 1, that's going to be 1. So when it is 1, this is 100% a point, and then as becomes larger, when output is becoming very larger, and you'll see so the graph approaches almost, the output is almost becoming almost 0. So when x approaches to a very large, infinite, a very big positive number, then the f of x approaches almost 0, but in the positive. So almost 0 but positive. But as this side, you will see as x becomes very tiny, smaller number, like goes closer to 0, but on the positive side, so you go at 0.5, then 0.4, 0.3, 0.2, 0.1, 0.0, and so on. So the moment you go closer and closer to 0 here, the output you will see. So output is, that means the f of function f of x. This function that is 1 over x, almost the output approaches close to 1, but not exact. This is just closest to 1. So that's all it is, understanding of the graph. And we can see this also, I will show on the graph how that works. Let's move another one. Next one is gx. So what do you think will be when gx? So this is, again, you can see, let's put it like g of 0. We cannot, this is undefined, right? So we can't have 0 not defined. Okay? So can we think of smaller number, like what is g of 0.5? So that will be like a half, right? So it is like 1 plus 1 over 0.5 and raised to 0.5. And you will see that that answer will be uh, almost like, so if you have something like this, let's see, this is 1, this is 2, and this is 3. Let's see, 1, 2, and 3, and 4, like this. That means the number, this approach is almost this one. When x is almost 0, this approaches uh, to, it approaches to 1, but not, it doesn't become 0. And you can see if I put, let's see, the 1, if I put a 1 here, 1 over 1, and then you put 2, sorry, 1, that becomes 2. So 1 is 2. So this will be 2 like this. If I put 1 over 2 raised to 2, that becomes 1.5 square, which is 2.25. Like this. So, and you can see this become 2.5 will be somewhere here. And likewise, if you go on checking 3, 4, 5, as the numbers become very, very large number, you will see a nice pattern there, and you'll see there's there is a one dotted line I'm going to draw, which is 2.7, where so you will see there's a line here which is 2.7, and all this red color, there will be there will be a graph which has is it a very large inputs for x. So this is almost coming near to that's like a horizontal asymptote. So if you see this as x approaches a very large positive infinity number, then this gx becomes almost close to 2.7. Of course, going to be 2.718. This, which is around, which is the approximation of the Euler's number, which is E, which is 2.71812, and we will see that also in the graph. And that means on this side, we will say as approaches very tiny positive number, like close to 0, it means you are making zero point 0.5, zero point 0.2. So x approaches very close, and you can see the output, these outputs, they're almost uh, closing into 1. So that means the g of x, so here, the g of x is approaches to 1. That's it. So this is the understanding. So clearly you can also see this piece is very important when the inside denominator becomes very large, and this x is large. This inside becomes smaller and smaller, okay, and this become larger. That's why it says the topic is 1 plus tiny is and large. So what is that? So this piece, gx is a special function which is for large positive inputs will give you. So the gx, so this gx here, this is the one, is equal to a. Okay, that's the Euler's number. Let's move on to another one. So now that we know that e is like 2.718 and so on, so if you want to graph this, okay, if I want to graph, let's see, if it was e raised to 2 raised to x, if I draw this function, and if I do this way, and say 1 and 2, when x is 0, if I put x equals 0, this whole thing becomes 2 raised to 0 is 1. So this is the point for that. And when I put 2 raised to 1, it becomes 2. So 1 is 2 like this. If I put 2 raised to 2, it becomes 4. So 2 is 4 like this one. You can see the graph for y equals 2 raised to x goes something like this. But if I write y equals 3 raised to x, so we can put 3 raised to 0. If I put 3 raised to 0 is 1. So that also is that also will give you 1. So this is again 1. But if I write 3 raised to 1 is 3, so 1 goes to 3 like this. So this is the graph goes something like this. This is 3, this will go like this. But then what about if I use e raised to x? So you see the graph, I'm going to use the black, uh, blue. So we'll see this is y is e. So this e basically what I'm talking about is it is 2.71 raised to x. So anything raised to 0 is, so that's one blue, this is 1. And if I put 1, so if I put h of 1, this is going to be e raised to 1, which is actually 2.718 raised to, which is 2.7. So I'll round it to 2.7. So if it is 1 here, 2.7, this is 2, this is 3. So 2.7 will be somewhere here. Somewhere here, maybe. Not perfect. I'm just trying to. That means you have a graph like this. So which is between. So this graph it goes between this way, in between like this. So which is the exponential function. The main thing is what you notice here is when you make x very small, tiny positive number, this means very small, tiny positive number, and you see the hx almost approaches to 1. So that's the 1 here. Okay. It- but if you so next is what about when x approaches very large positive infinity, a very large number, and you can see this graph it goes on increasing faster. This is why equals 3 raised to x. I said this goes little slower, which is 2 raised to x, and this one is little faster than 2 raised to x, but slower than e raised to x. So that's the answer. The output becomes, so this is the output y-axis, the output becomes very large number. So all we do is write down here that hx is approaches very large number also. So hope that helps to understand this piece. Okay, this is the last one, kx. Kx is 1 plus x. Now what is this 1 plus x is? Starts at 1, so this is 1. And this is of the form, you can write it as 1 of x plus 1, which is like a form y equal slope intercept form, where that's the y, that's the slope, which is 1 over 1, because it is 1, so it is 1 over 1, and that's the y intercept, so that's where it starts. So if I can do this way, 1, 2, like, so you can just draw the line. So it is the line going this way. So the 1 is 1. So when x is 0, it's going to be 1. So it goes 1, 1. See, you 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 move to the right. Let's see, if you for increasing x in the input by 1, it goes up. And again you increase 1, it goes up. So and like that. See. So you get a line like this. See. So you go, this time you go to the left, and then you go down. You go left, you go down, and so on. That's the line. So what is important about this line is as x approaches very close to 0, but positive side, and you can see it's touching. See, of course, we can just put a 0 is 0. 0 will be 1. So that means your k of kx value is going to be almost equal, is 1. So this approaches, that means for tiny values of x, the output will be approaching to. So if I take x very smaller and smaller and smaller, almost close to 0, and the output will be, so this output, they approach to 0. Now this is very important because there is some relation between. So the second question is asked here is to remember that E is 2.718. What does the function g have to do with this number e? Now, what is the function gx? So gx is 1 plus 1 over x raised to x. So what this function got to do with this number, right? And you can see when you graph this, we saw that when x is almost 0, then this is almost like 1, but the graph goes this way. See? So this function gx approaches to 2.718 to the output for large value of x. That's all it means. Understanding that. Yes. Then question number 3 also says. Question number 3 says, what's the relationship between. So if you see this, the third question is asking us. Where the third question says, what do you notice about the relation between h and k? So the function h, what was hx? Hx was, uh, I think hx, let me see, hx, oh, it is e raised to x. How are these two compared, this kx and hx? And if you see that when around 1, so this is 1, when x is approaching closer to, x approaches closer to very small positive z until 0, then you see this answer kx. So kx approaches almost close to because it's going to be very closer to 1. And I'm going to show you with the table also and same. And also we have seen this graph e raised to x, even though this graph we have seen goes this way, right? Something like this. So at 0, x, the answer is 1. Okay, so this graph also, the output almost are approaching to 1 when x is. So that means, let me draw two lines here. One line is this one, which is this piece, and the other line is the this one. See, so 2.7. So something like suppose I put 2 here, and maybe this is 2 and this is 3, 2.7. I'm just trying to. So when it is 1, it is 2. So this is going like this. So this graph, so this is when it is 1, it is like E, which is 2. So this graph, something goes like this. So not perfect, but just trying to see if I can do that. So this is approaches to x. It's like a x-axis becomes like a horizontal asymptote here. So the kx, the linear form that you see is approximation. So when x is for smaller values of x, so the pink color and the red color is almost the same thing. Let me use, so this one approaches to 1. See, this one also approaches. So for a small value of x. So for small values of x, both kx and hx approaches to 1. So the value of x, both h and k approach. And later on in the later classes, you'll also learn what is that the important concept of Maclaurin series, where you will see that e raised to x can be approximated by, let's say, right now it is approximated by a linear form that is 1 plus x, but you can also approximate with the help of cubic function. You will come across x1 plus, sorry, quadratic. You can write x squared divided by 2 factorial. You can also approximate it by 8x1 plus x plus x squared and over 3 factorial. You can also use e raised to x with the help of a quartic function like 1 plus x squared over 2 factorial. I think I missed this. Then x cubed over 3 factorial. And then x raised to 4 over 4 factorial. And likewise. So these are the things like how we can, for each function, we can create a polynomial function for the function. So this is called series. So series, which is also we will write like this, where x raised to n factorial, and this is n when n equals 0 to infinity, something like that. So a lot of that will be done in calculus B. This is just a start to understand. I'll just go check the Desmos and see what we did is. So I try to put this in the uh, okay. Watch this. Let me. The first one was a raised to x, and you can see this. If I click here, you see the number line. That's the first one. The second one was the this one going through this, so you can see clearly. This is the rational function d. So I take off this, and you can see when x approaches to 0 here. So when this x approaches to 0, then the output becomes plus infinity. It becomes very large here. And when x approaches very large, then this whole thing, I think I forgot about this to show that why this is a rational function. We have seen for a small values, positive value, the output becomes very large. And for large value, this way it goes. You can see this also. You can trace this and you can clearly, the more closer you go, the first number that x value becomes almost close to 0. And you can do this way. You can say the more closer you go, the output is becoming very large. And the more bigger number you take, the output becomes very, very, very small. Okay, so I think I forgot to show that. Next one was this piece. We have also seen on this piece how, look at this. So this one, if I try to, this is for 1 over x raised to 1. The more smaller values of x, you can the output almost become 1, but doesn't become. So that's the even though it shows here, so this part 0, you can't put x is 0 here, you can't have a 0, but that's close, almost approaches to 0. But then it goes, when x becomes large number, you can see the output becomes very, very smaller and smaller and smaller. The more bigger the input is, it's going to become large. The next one, I made 3 tables here. So let me take up this and see this piece. So for this, let me click here. You can see the graph clearly. What I was talking about is, and let me make it look at this. So this graph for small values. So what I put is 0 point. Let me start with 10 here. So this is the 10, and if I click here, I can see the 10. Uh, 10. I'll have to push this I think, so make it smaller maybe. So that's the 10. See? So 10, and then the more closer now I make the x value 7. See? So the value, the output becomes smaller and smaller and smaller as x makes 3. Now see x is 3, 2, and the output is going slowly decreasing. And the more the output the input becomes almost like a small number, see, the, the answer is going to be here, right here, which is 1. And that's what I wrote here. The smaller the x is input here, and you can see the output is almost like close to 1. And the larger the numbers, if I put 10, 20, 100, 1000, 10,000, this number approaches to 2.718. So I can just put the equation here maybe. Uh, maybe I can. So, okay. So this values, you can see that's the number it approaches to Euler's number 2.7181. Let's let me take off this. And hx is e raised to x. So this is the one. Okay. So e raised to x, here it is. So e raised to x is for small now. When x is 1, you get 2.7182. When x is, so the smaller this, you can see this piece, the more closer, tiny positive value, and the answer is almost like 1 point, almost like 1. So this graph approaches to 1. See, this is almost like 1 here. Of course, when x is 0, it is 1. And the difference that I also did for kx here. So kx 1 plus kx, I already showed you. What I try to do is we want to compare this. That's what is. So this, if I want to check, look at this beautiful graph. Kx, and there's a line. So that's the line. This is the line. And both of them, 1 plus x, this is 1 plus x. This is almost approximation for e raised to e. This is e raised to x. But then look at this. What I did is I tried to write the Maclaurin series. Let's if I take a quartic, so if I see the quartic, and you can see almost equal close, so near the 0, x is 0, the green graph, you can see this piece is almost the same as the e raised. This is e raised to x, so more approximate. And you can even make it more approximately by adding another one if you want to add plus x to the power 5 and divide by 5 factorial like this, and you can see it's more better than almost e raised to x. So this is the black color graph. So this is the black color graph. This one hx is the black color graph. But then the green graph almost superimposed on that near the 0. So this is near the 0. So almost same thing in the neighborhood of 0. So you will see that the graph, green graph is same as the black. So I hope that helps to understand this piece. Then I was talking about one more is they ask you about So comparing this. So there was one, are you ready for more? And you were supposed to fill this up. So what I did is I put the input as 0. This is what is given to you. 1, 2, 3, 4. And these two pieces are given. This one and this one. The rest you are supposed to figure put. So using the calculator does the job. You can see, let me take this off here. Okay. So now this is the graph for y equals 2 raised to x. This is 2 raised to x. So this is 2 raised to x. Then I have 3 raised to x graph. I have to write here y equals 3 raised to x. See, that's the blue one. And now I want to write e raised to x. So I'll write y equals e to the power x. And in between, see the green graph. So when you see this, the goal is what's happening is, and you can see all these three graphs that you see, the blue, green, and the purple, they almost approach to one. See all of them. So what I'm trying to say is, so this graph y equals 2 raised to x. Let's say this one is y equals 3 raised to x, and in between this green one is y is 3. They all the output, you see the outputs, all three of them approach to one. So for smaller input x, input positive x, all three. Now, when I say all three, I mean I think it talks about 2 raised to x, e raised to x, 3 raised to x. They all approach to 0 point, sorry, approach to 1. That's it. That's understanding now. One more thing you have to also see is, there's one question they ask is, what do you notice, and what is the main thing about what do you notice about this last piece? This one, when x is very tiny, small number, this is almost like 1 plus 0.0001. It means, remember there was a function, I think it was hx. So 1 plus x, which was kx. So the kx was 1 plus x. Okay? And this is for very, very small number. And the e raised to x was, you see on your thing, e raised to x. So this e raised to x was hx. So that's hx. So hx and e raised to x is the same thing. So this part, these two are the same. So this is e raised to x is hx. Okay. And you will see this number is almost this uh, kx, k of 0.0001, which is 1 plus. So that's the understanding is, that the more smaller the input is, then the value is, the e raised to x is almost same as 1 plus x. I think I made a point. I hope this helps. With this, I want to stop this, almost like a 1 hour video, but hope that helps. Thank you for watching, and I'm posting this in the YouTube channel, putting the link in the classroom. So those of you who missed the class, this will be very helpful. And those of you who couldn't understand this, you can watch it one more time, and play and see how it works. Thank you very much. The next video will be on lesson number 13.